again, this intelligent adaptive experimentation and how can we use statistics and machine learning to accelerate science and help people. So let's welcome.
Thanks, everyone. Great to be here, and thank you so much for having me. There's one thing I have to tell you before I start that's very important. I'm from the Caribbean, from Trinidad and Tobago, and I have to tell you this because people say that they miss most of my talk trying to guess where this unusual accent is from. So I'm from Trinidad, full attention for the talk. One challenge is that I speak very quickly, and Trinidadians also speak quickly, and an accent makes it harder to hear. So it'll sound like 8 times speed. So help me out, please. Just wave your hands, 2 hands in the air, if I can slow down, and interrupt anytime with questions. It's my New Year's resolution to speak more slowly, but it's a very hard thing to change. So as I mentioned, the work we do crosses many disciplines, right? And I have 2 PhD students in statistics, Tong Lee and Fred Houchin Song, they're in 2nd and 1st year. And so I'm going to focus a bit today on the work that's been more statistically focused, right? But there's probably 20 or 30% of all the work we do. There's a lot of other work in areas like human interaction, how do you design software to help people, like design visualizations or sending people emails to get them to change their health behavior. And you can always read more about that on my website. Okay. And also want to say that anyone's welcome, any grads or any faculty, to join this mailing list. tiny.cc join IA extended. That's like a short URL you can type into your browser. And you can basically be on an online lab mailing list. And it's a way that you can hear what's happening and pop in if you're feeling like it, or just offer to can I try out a practice talk? Can I try out an idea and share with it, like what we're doing? Because we're trying to think of how do we do research in a scale where to solve these real world problems, like designing software, helping people, you really need to bring together different disciplines. So how do we do that more efficiently? Right. All right, so I'll jump in then. So as Frank said, the title of the talk is Intelligent Adaptive Experimentation, integrating statistics and machine learning to accelerate science and also help people. So fundamentally, I think a lot about decisions from traditional experimentation and adaptive. A traditional experiment might be assign people 50%, 50% to get explanation A or B in a statistics class. And then the outcome might be whether they say it's helpful or not. But our goal really is how do we increase use of data to inform more real world decisions? In general, do we give a person experience A or B? Email A or email B to see what they respond to? Text message A or B to see what helps them learn about cognitive therapy to manage stress. These are all examples of the 100 field experiments we've run in the last 10 years. For you all, how would you test ways to make your website better? How do you modify a website to get more clicks on your papers, which we're all very motivated to have? In a traditional experiment, you would randomize something like 50-50 to an arm or condition or version A versus B. You'd analyze data, and you have to make that decision when to stop. You switch from 50-50 to 0-100. But this is the 21st century, and it's kind of strange that we haven't modernized or changed our approaches to experimentation in so long, especially when we go from traditional experiments in a lab or field trials. How can we reimagine it through software? In an adaptive experiment, what we might do is change the probability of assignments adaptively using the data that's being collected. For example, you assign someone to explanation A or B, or website A or B, and the outcome is whether they click on a link or find it helpful. As you've got 30 data points, 60, 80, you might modify the probability. What's the posterior probability that A is better than B? If it's 70%, could you assign with 70% probability? If it's 80%, could you assign with 80% probability? Do you all kind of see how you might think about that kind of paradigm? And that's just one example of the many ways you could do an adaptive experiment. And what's our goal as we change the probability? Honestly, that's part of what we need to do research on. But one goal you can have is, why don't we figure out more clever ways to trade off the practical benefits to people in the experiment, so you get more people clicking on your papers because you get them a better version of your website, against scientific benefits. And I mean here, knowledge. You get knowledge with a certain confidence about whether there, in fact, really is a difference between website A or B, version A or B of your website, or explanation A or B of a concept to help students learn. that make sense, people? That's the high level kind of vision. And here's an example that I'm going to focus on within this talk. One particular machine learning algorithm for what's called a multi-arm bandit problem. And let's call this posterior. You'll see why it's in quotations later on. Posterior Thompson sampling. And the kind of key idea is, again, using an example, if you're saying explanation A or B of a statistics concept, so explanation A of what a z-score is, explanation B of what it can be used for, and your outcome is whether people say that was helpful or not. What if you assign that explanation A or B based on the changing posterior probability that the proportion of people who say explanation A is helpful is greater than the proportion of people who say explanation B is helpful? Does that make sense? You have some estimate, you have some idea of what the true population mean for A or B. You've only got some imperfect understanding of that. So let's assign people to explanation A or B with the changing posterior probability that in reality, it's got a higher sample mean, a higher portion of people think A is helpful. Does that make sense to everyone? That's kind of the fundamental algorithm approach we're going to look at in this talk. And you can see example, 50-50, 70-30, 90-10, and changes over time. And this opens up a whole bunch of directions because you can imagine as something starts to look better, like if you think there's a 90% posterior probability that explanation A is better, then you might say, well, why don't we actually phase out B and add in a completely new explanation, an even better way of explaining what this looks like based on qualitative analysis or instructors' judgments. So why would this be a beneficial thing to do? Because the idea is this floating around forever, right? Practical benefits. We can use data to help participants. So we could actually run experiments in the courses you're taking right now and use that data more quickly to help students learn. Also, it could make practitioners, as we've shown in some of our papers, like instructors, more open to experimentation. Because experiments to them is not just something a experimental psychologist or education researcher wants to run, or statistician, it's actually a practical tool. There's a chance that data will help them. And if we can increase the number of experiments people are doing right now, there's a high chance we can get people using data to improve decisions. So the potential for adaptive experimentation to increase people using experiments to make decisions about what might or might not be effective. Scientific benefits are, well, the challenges with these traditional experiments. You only adapt in a dichotomy. You're 50-50, then it's 0-100. So are there benefits? Can we explore what these are to gradually, probabilistically phasing in assignment? Because if you think about it, I mean, sure, you can run it for a particular power analysis, 800 participants, do a z-test, and, you can choose an alpha, a type 1 error, a false positive rate of 0.05, 0.01, and stop. But of course, we all know that you're not totally sure, right? So why are you stopping your experiment completely, even when you're unsure? So maybe a bit of a radical kind of way of thinking about it. It was radical to me years ago. But what if we actually don't just run experiments and stop, bam? What if we could actually explore methods for continued data collection in proportion to uncertainty? In proportion to how sure we are, there's a 90% chance it's better. Let's keep collecting some data so we can become even more sure. If you relaunch an experiment in a new context, right? Do you do it from scratch? Or could you in some way think, well, I'll relaunch it instead of 50-50 with 80-20? So hopefully that makes sense in terms of the value of scientific adaptive experiments that they may have. That's what we need to do in this research, is understand what the value is and when it's helpful of continued data collection in proportion to uncertainty. This also requires some reimagining of how we use experiments. I think that's a big theme of our lab, which is how do we reimagine what we use experiments for? How we think about them, on what value they can bring practically and scientifically. Because you think about this more in terms of continually adding and removing ideas. For example, instead of just saying, let me run an experiment because I got funding about whether explanations that are simple are better than explanations that are complex. You run it, 800 people, you report it. This is more like an ecosystem. Right now, you're all in classes. Those explanations you're getting of a concept, the emails you're getting, you could experiment on those for years. Those could be intelligent systems that keep improving. Every semester, there's a new experiment. There's new ideas. Sometimes you bring back old ideas you thought weren't effective, but actually turns out they are in some particular context. So if you all see how adaptive experiment could allow us to keep removing and adding ideas. Because we're now experimenting in the real world on something like an explanation website that keeps improving over time. It should never stop improving. What explanation is really good enough? What website's really ever as good as it could be for everyone? And I'm sure there are other opportunities here to more generally think about this integrated framework for how we're making data-driven decisions by embedding experiments in the real world. So it's clear what the practical benefits and scientific benefits might be. And I will say, to put a different way of thinking about this, the vision here is, to tie some machine learning, is how do we turn components of websites, apps, emails into intelligently improving systems where human beings are adding ideas. Every time you see a website, you make a suggestion, could enter the experimentation chain. And you've got algorithms, machine learning, and techniques from statistics to keep testing out these actions and using data to improve. Because in a way, this is what a human being does. Every year, teachers keep testing out different ways of explaining, getting data, and changing what they do. How can we augment what they do? How can we have our software be as dynamic and adaptive in that way? Still on that vision, all these intrigued? Well, now I have a question for you. Well, what do statistics and machine learning researchers have to do to support that? This is a very rough characterization, but in terms of current state of adaptive experimentation, which could be 100 different things, but at least the approach I talked about in terms of assigning people in proportionate probability, this may be the best arm or condition. Some algorithms are actually used by teams and tech companies. Like a lot of what makes Instagram and Facebook and so on so compelling is that they use these algorithms to try and identify, in some contexts, in some products, what's going to engage you. But we're using algorithms to get people to click on ads. Why don't we use them to help people learn or deal with mental health? And again, some algorithms used by teams and some tech companies, so I hope those things are reliable. But also others aren't even aware of it, or they're wary. How does this affect statistical analysis? Does it throw things off a bit, a lot? And there is increasing use in sciences, social behavioral sciences, but it's not standard. Maybe there are huge opportunities if everyone could run these experiments constantly. We could speed up how many ideas we test and how scientists build on what people have discovered before within the same paradigm. Everyone's testing out explanations in someone's course, and you have hundreds of scientists opening ideas in and building upon what they do. This is actually what we have a grant for, providing tools for people to do that. So I think we need to better explore both the limits and opportunities of adaptive experiments and define different classes of those. So in this talk, I'm going to discuss examples of these broader themes of our research. One, how do we empirically explore? How do we quantify and understand these statistical trade-offs in particular applications? Two, what we call algorithm-attuned statistical tests. How do we develop statistical tests that benefit from knowledge of the algorithm adapting experiment? Whereas most statistical test experiments are based on assumptions that it might be uniform at random, 50-50, or a traditional experiment. Three, how do we have more statistically attuned algorithms? How do we and machine learning researchers develop algorithms to collect data that better trade off the statistical analysis against reward? And by reward here, I mean helping people. Reward is the positive outcome when you give someone the explanation that actually is higher rated or helps learning more. That makes sense? And I think there's a lot of potential to transform how social behavioral science is conducted in the real world. People are now moving into the field, or even if they've been there for a while, we can help them do it better. How do we expand the practical impact of economists, political scientists, psychologists, educational researchers? How do we expand the number of experiments that are being run to use data-driven decision-making? Nature of field experiments in areas like human-computer interaction, which is designing software to help people, testing out websites, building ways to get people to change their health behavior through text messages or apps. Everything you touch today is software, right? Other areas like economics, psychology, health behavior, political science, communication. So is that clear how there's a lot of potential to transform? And many open questions. And this is a long introduction. I could stop here if you all were so or excited and worked on this. This requires a multidisciplinary approach. And in our work, at least, we have colleagues who are computer scientists, biostatistics, economics, statistics. How do you combine stats and biostats, machine learning, human-computer interaction, how we build the system, psychology, education? And a lot of our work has been actually looking at real applications. In 2013, 2023, over 50 field experiments, including education, health, and other areas. And I would say that so far, it's had a lot of impact in the sense that right now we're top 3 finalists in X Prizes $1 million challenge, which is for the future of educational experimentation. What's the future of educational experimentation infrastructure? How do we modernize the way educational researchers and practitioners collect data, given updates in machine learning, AI, or just the way we use software today? The fact that everything's online. Have we already got the benefits? And I think what's especially exciting for people here is we were awarded this across many universities, $3 million NSF grant. This basically building software tools and community for adaptive experiments, which will connect social behavioral scientists with instructors and other practitioners and statistics researchers and machine learning researchers to run adaptive experiments, proposing experiments, putting them in the field, testing algorithms, coming up with statistical analysis techniques, hypothesis tests, Bayesian analyses. So you can actually get data sets and test algorithms using these tools. Or you can just practically use them to test out which emails you send to people to get them to respond to you. And as I mentioned, this is our group here. And so I have 2 grad students in statistics, Fred and Tong, and others in human interaction and also in psychology. Okay. So let me give you the algorithm or the approach we're going to focus on today in the work I'm going to present. This is doing adaptive experimentation via what you can think of as Posterior, or it's also called Thompson Sampling. And this is the algorithm that's for the multi-arm bandit problem, which is one of the most fundamental forms of reinforcement learning. You can think of it as like randomized probability matching. That's what I mentioned before. I'm going to talk about this with a beta-Bernoulli Bayesian model with the 2 arms, binary reward outcome. 5-6 years ago, I was working on much more complex problems, and I did not realize, it took me a while to realize how this problem is not even properly solved. Even talking to dozens of researchers, some of them think it is, and there are some big obstacles. And if we can't even sort out these statistical issues for 2-arm binary rewards, then that means that they're like challenges that are looking underneath everything else. And I think we could solve this. This will have a lot of impact. So what's the problem setup? You have a set of actions, arms, for example, explanation A or B. You have a reward thing you're trying to optimize or an outcome. For example, was the explanation helpful for learning? 1, yes, 0, no. And you have a policy or policy learning algorithm. And for posterior Thompson sampling, the idea here is that you're assigning people by sampling proportional to the posterior probability based on the data so far and your particular model, that this is actually the optimal arm. For example, that the proportion of people saying explanation A is helpful. Is it 0.3? Is it 0.4? Proportion of people saying explanation B is helpful, 0.6, 0.7. What's the probability, given data so far, that that proportion is higher for explanation A than B? And so you can imagine the kind of simple but I think fundamental, beta-Bernoulli model. So the probability of an explanation being rated helpfully, probability of an arm generating a success follows a beta distribution with parameters alpha and beta. And then you have a Bernoulli likelihood, where the reward is drawn with the prior that comes from that beta. And so you have a beta for each arm, and Thompson sampling essentially samples those parameters and chooses the arm that from that sample maximizes the reward. So basically, in this case, it's simple. Draw 2 betas. If you have 0.6 for arm 1, 0.4 for arm 2, you just pull arm 1. And that simple heuristic does a pretty good approximation of sampling in proportionally posterior probability. Okay, let me speed up a bit. So adaptive experimentation is a broad problem across many fields. There's work from a machine learning perspective on BAN algorithms. There's work in adaptive clinical trials that have tried different kinds of approaches. Statistics, biostatistics, economics, operations research, technology companies doing A/B testing, behavioral scientists, practitioners who could use these techniques. So in terms of what I'm going to present, I really spent a lot of time trying to explain the practical and scientific potential of adaptive experiments and what they are. And at least the particular algorithm we're going to focus on a posterior Thompson sampling. And we present results about empirically exploring what are these statistical issues that come up in adaptive experiments, even for that two-arm case. We'll see an example of doing algorithm-attuned statistical tests that are tuned to how the algorithm adapts the experiment. What are statistically attuned algorithms? Algorithms that are tuned to trading off reward, helping people with statistical analysis. And they can get in some ongoing and future work in terms of getting more accurate posteriors, because spoiler, the ways that the algorithm runs actually are problematic. And how do we tie these ideas from optimal experiment design versus just techniques from machine learning that are more designed to just optimize or help people? And let me give it away what the kind of key results are. In terms of empirical exploration, for two-arm binary rewards, Bates-Bernini model, if you use, like, for example, Wall z-test, as well as many other methods, and you run an adaptive experiment, side by side with a traditional uniform random equal probability experiment, you actually get increased false positive rate or type 1 error. It can go from the 5% alpha level you set up to 13%. And you also get reduced power, where you get a power that goes from 80% for a particular sample size that drops down to about 57%. And I'll say a bit more about why that happens. But when there's no difference in arms, and using this posterior sampling, when you have random loads, what happens? You stop sampling. And so you can get biased estimates of a sample mean. They're the exact same, but when you have a random low, you can stop sampling. And what that means is that you basically will get a higher rate of false positives, type 1 errors, because you will see differences more often when they don't exist. And you can get lower power because you put more participants in one arm. It may be better, but you're not sure if it's better. Why that's especially problematic is because this way of thinking about the assignment of posterior probability, when there's no difference, what happens? You don't get a nice normal distribution where it's around 50-50. It will converge on one arm. And the reason why is that, again, as you get random lows, you will stop sampling. So much more often than you would like, it will end up putting more and more participants into one arm. So in a way, you can't quite, those posterior probabilities, you can't quite trust them. Yeah.
But if the two arms are identical, then does it really matter which one you pick? I mean, then it doesn't matter. I mean, what you really want is what if one is strictly better than the other, then you want to pick that, right?
Yeah, so this is a great point. And this is like, there's several papers that point this out. If the arms are the same and you're an instructor, you might say, well, I don't really care, or a company, because they have the same outcome. And that's a reasonable under a particular model where you think, I don't care about reward right away. But where could that go wrong? Suppose, for example, you run a test in your class showing that video explanations look like they're better than text. And you run this algorithm, and you put 95% people in video. And then he says, well, great, I use video too. Now you've spread some false knowledge that is actually making you do something that may be inappropriate and costly. Does that make sense? Where those false positives are problematic because one experiment can then influence what people do after you. It may not matter for people in the experiment.
I guess there are certain situations where the model might not capture everything about reality that, you know, then in practice you might want to consider. So that I definitely
Yeah.
But just in terms of the model, like
No, I think it's fair point that, like, this is why I think this is such a people aren't necessarily tracking this approach, which is practically you may not care that much in the setting if your outcome variable is good. But in terms of acquiring knowledge that then misleads other people, or the reality of the real world is you want to run sequences of experiments. That's when it's a problem. So it's a good distinction. So the second part is still thinking about algorithm-attuned statistical tests. And so we'll talk about how if you're varying the posterior probability of a posterior probability, if you're using posterior probability to vary the assignment probability, then you can imagine adjusting things like a Wald z-test statistic using inverse probability weighting, where you kind of use inverse probability weighting to weight your estimates of the sample means. You can also use what we call an algorithm-induced test, where you simulate under the null the wall z-test statistic, P1 minus P2 over the standard error of the difference. But you don't just construct a normal distribution as you would if it's collected with uniform random. You say, well, if I assume the null and I'm using Thompson sampling, how does that change the distribution of my test statistic? So you can then actually adjust your test, the algorithm-induced test, adjust your test statistic, the wall test statistic, by changing the cutoffs. And that helps you control false positive rate, but it has a huge impact on power. IPW does eliminate bias in the estimates of sample means, but it doesn't actually help much in terms of hypothesis testing, and we think it's because it inflates the variance so much. What we'll introduce at the end, though, is work we're doing now on what we call an allocation property test. I think this is very exciting. It's a new test statistic that defines not difference in R means over the standard of the difference. It defines a count of how often the assignment probability of this Thompson sampling algorithm is above 0.5. For 1 R, count the number of times the assignment probability is above 0.5. And this test statistic actually gives much better discernment. It allows you to control false positive rate or type 1 error, and it also gives you better power. Then finally, I'll talk about statistically attuned algorithms. And here we're going to investigate hybrid combinations of traditional uniform random experiments, as well as reward maximizing bandit algorithms like Thompson sampling. And this algorithm, which needs a much better name, so please suggest, Thompson sampling posterior difference. What it does, it says, epsilon of the time, let's assign with uniform random, 50-50. 1 minus epsilon of the time, let's just run Thompson sampling, posterior sampling. So you will see it's combining uniform random with Thompson sampling, which could help mitigate some of the issues with Thompson sampling. But what's that epsilon? We're going to compare a fixed epsilon, but actually the key idea here is let's make that epsilon uniform random proportional to the probability that the arm difference is small. Small is a parameter chosen by a scientist or a practitioner like an instructor. But for example, if she thinks 0.1 is a small difference, if arm 1 is 0.4 and arm 5 is 0.46, that's small enough that I don't mind actually not getting reward. It's okay to give people an arm that's not that good because 0.1 is small. I would much rather get a good false positive rate and good power. So it allows you to say, here's a small difference below which I want to trade off and get more statistical inference, false positive rate and power. But if it's above that, actually I want to maximize reward. And I think this is an important addition. There are pros and cons of all these approaches, which people have to decide in different contexts. But I think there's an argument better balances reward and power. Because when you have small effects or non-existent effects, you get more uniform random. But when you have big effects, you can then maximize reward.
How do you generalize the allocation probability testing more than for?
Yeah, that's a great question. That's actually, we could talk about that after. Yeah. Great. So I'll start on the empirical exploration. So you can read that paper on arXiv. And we're writing this for machine learning audience right now. So as I mentioned, this is the problem formulation and the algorithm Thompson sampling for beta Bernoulli. And so we basically compare uniform random with adaptive experiments. I use false positive rate to speak to machine learning audience as well as stats and power. And here's 2 examples. We have many more in the paper. Arm 1, arm 2, 0.5, or an arm difference of effect size 0.1. Kind of what might be standard in some behavioral applications. 0.5 is 0.55. Here's the wall z-test, the test statistic. P1 minus P2 hat over the standard error of the difference in means. So that's the test statistic we're using. And as I mentioned, the false positive goes from 5% as much as 30%, power from 80 to 56. And it isn't just to that test, right? The wall test, you can look at just t-test. You're seeing a false positive rate, power for Thompson sampling, it's uniform random. If you try to use Bayes factors of different kinds, so it's a pretty persistent problem. It's not just a simple adjustment to the test. And here's one of the reasons why. why do you have this? A false positive, here's an illustrative example in a similar experiment. When there's a true line difference, random lowers leads to reduced sampling of the arm exactly when noise suggests it's worse. So you get a bias estimate one lower arm. So P1 is blue, P2 is orange, and green is basically posterior probability of assignment. So you start assigning 50-50, and then you happen to get a higher estimate here and a low estimate here. It jumps up. But what you can see is the probability stays high, and it actually will converge. Because even though you're putting everyone in this arm and you get more and more accurate, it's not as high as you thought. This doesn't really recover. Is it clear to people what's going on there? That the random lows you don't recover from in the long run, even with infinite amount of data, because you get more and more sure when standard error gets tight here compared to that. And so it happens about 30% of the time compared to 5% uniform random. Now, of course, if you look at the posterior means in the beta distributions, well, they're also biased. Because for this case, the sample mean is going to be the posterior mean. Why do you get a false negative? Here's an illustrative example. Even if one arm is higher than the other, as you can see here and here, you might assign people here, and then your posterior probability of assignment goes up. So again, you can get a tighter standard error on this one. But even if there's a difference, you can't actually get a good estimate of that arm mean. So you don't know for sure. And why is that especially problematic? I'll come back to this in a second. It's problematic because with the bias posterior probability favoring one arm, even when there's no difference, a high assignment probability doesn't provide a lot of evidence. Even when there's no difference, assignment probability is really high. So if you look here, right, that's in 10,000 simulations. With the assignment probability, the superior arm, the arm with the higher sample mean, how often is it between 0.5 and 0.6, 0.6 and 0.7, 0.7, 0.8? Well, even when there's no difference, right, portion of simulations that have assignment probability that's 0.5 and 0.6 is 15%. But when there's no difference, the assignment probability or posterior probability will be between 0.9 and 1, 33% of the time. Does that make sense to everyone? Like what you might have hoped for would be that they'd be clustering around here. When there's no difference, the algorithm will lurk around 50-50, 60-40. But actually what happens, it tends to converge on one arm. So you end up with a situation where everyone's in one arm, and the posterior probability is that its arm is better, but actually that's happening disproportionately often when there's no difference. Now, of course, there's some hope, right? Which is when there is a difference, that number is much higher. So it's 87%. So that makes sense to people in terms of how, at least this way of doing the posterior, it causes an issue because it's putting people in arm because of things like the bias and sample means, and you're disproportionately confident that arm is better. I will give you a quick teaser that this is essentially the idea of the allocation probability test, right? Which is you can't take the posterior probability as it is, but you can construct a statistic that says, let's count the number of times the posterior probability for arm 1 is greater than 0.5. And then you can get the distribution of that under the null. And so as you can see, there are more extreme values when there's a difference versus when there's not. And I think what's clever about that idea is it's more sensitive than using something like a Wall-Z test statistic. Okay. So what do people take away from this? This gives a sense of how that detailed empirical exploration using simulations as well as data drawn from the real world shows the issue with increased false positive rates and reduced power and why that happens. Random lows cause bias estimates. You get convergence. Even when there's difference, you can't get high power or certainty about it. And the assignment of posterior probability substantially favors one arm, even when there's no difference. In the most simple fundamental case, and it's surprising how much this is overlooked. Like I'm actually shocked. Lots of theoretical work on bias and so on, but laying it out in this particular context and showing the kinds of things that a social behavioral scientist might actually run or Webster experiment would actually run. So my talking slow is going well, but it also means I'm getting short on time. So let me think what I can skip ahead on. So in this overview, how about the second one? Algorithm tuned statistical tests. So maybe I will actually focus a bit on the latter two. And again, the key idea here is let's modify statistical tests using properties of the algorithm. And the problem is Thompson sampling changes the distribution of the overall test statistic relative to uniform random. So we can adjust the hypothesis test to account for the active nature. And we're going to skip IPW. It's not working as well as one might hope. I'll look at the algorithm-induced test statistic and the allocation probability test. Let's say you skim that. Okay. And so the challenge here is that this is the Thompson sampling induced distribution of the overall test statistic. So I can, yeah. So here you see the overall test statistic, P1 minus P2 with the standard error of the difference, and the uniform random assignment. This is where you get your chosen false positive 5% and power of 81% if there's a 0.1 difference, right? So you can see what that looks like. And you can see where the critical value of 1.96 gives you 5%. But now with Thompson sampling, what does it do? Well, when they're under the null, there's no difference. You get these fatter tails, as explained earlier, inflation of the difference that you see between arms. And so that same 1.96 gives you a higher false positive rate, negative 13%. Even when there's a difference, though, you also get the distribution being skewed back because you can't get extreme values of the test statistic because you have many participants in one arm, and also all kind of interesting complications. Just a secret looking surprise. You actually get an increased power by doing something wrong with Thompson sampling, but I'll say that for later. So does everyone understand basically what happens with how Thompson sampling is impacting the distribution of the test statistic? And so I think you all can see, a natural way to tackle this, right? Which is for any algorithm, for any statistical test, you can have this algorithm-induced test where you simulate under the null. In this case, it was 0.5 and 0.5. And you could also choose that based on your particular experiment. Simulate under the null, and then you just adjust the critical value to give you a 5%. So now you choose critical value from 1.96 to 2.6. So you get a controlled false positive rate. But what's your power? 17%. I mean, have you tried time behavioral science? They have a power of 17%. But we could do better somehow, right? And I will say the other tests have been tackling this kind of issue, and they try to improve power by doing something called probability clipping, where they don't let the probabilities go above a certain amount. Maybe at 0.9, you just can't go higher. If it says the posterior is 0.95, you clip it at 0.9. And those have interesting ideas. You can prove asymptotic validity, batch ordinary squares by Zhang, Susan Murphy, and others, and adaptively weighted augmented inverse probability weighting by Vitor Haddad and Susan Murphy and others. It helps with analysis and inference, but it reduces reward because you can't actually go that extreme value. So this new allocation assignment probability hypothesis test. And we're using the word allocation probability, it means same as assignment probability. So you get efficient inference without trading off regret. And we're applying this to Thompson sampling because it's one of the most widely used algorithms, and it's very intuitive and natural for other practitioners as well as scientists. And so it counts the number of times the Thompson sampling allocation probabilities for an arm are above 0.5. So just sum up for the number of batches you have or assignments. How many times is that above 0.5? And here's what I guess I'll give you a story. It does better in several ways. But here's why this is interesting, right? If you compare under the null, the Z test statistic, the overall Z test statistic, to the allocation probability test statistic, right? This is what it looks like, reflecting what I showed, that this algorithm will converge and tend to give actually like one extreme or the other. But that's under the null. Under the alternative, you get that spike. And so thinking of how to best characterize, explain this, but it's more discerning, right? It's giving you better discrimination between these two cases because it's sensitive to a property that's being used by the algorithm in the process of data collection. that make sense? So again, you set your alpha false positive rate based on that. And there's some corrections you have to do and so on. And so the paper has improved some extensive simulations. And so how do these tests compare? AP test, Bash earnings quiz, which as we mentioned, can improve power, but with probability clipping, it can reduce reward. And I'm not sure it's the case of one test will always be better, right? We're exploring the space of these options, and some are more intuitive than others for practitioners and scientists. But in this graph, what you're seeing here is this trade-off. A more extreme value is bad. So now we plotted, just to confuse you, opposite. Type 2 error, 1 minus power, right? Type 1 error, false positive rate. Regret is the opposite of reward. It's like how much worse you did than you could have done by giving people a good explanation. And also computational time. So what you see with the allocation probability test is that it does better in terms of power, right? Then, for example, BOS. Everyone controls type 1 error. And in terms of regret, it does better in BOS and slightly better than adaptive weighted, augmented inverse probability weighting. And in terms of computational time, it's also a lot more efficient and quick. So does that make sense in terms of how that test, by focusing on that particular aspect of information from the algorithm, the probability of assignment, can actually help you get better power and perform state of the art without having to change the algorithm necessarily. What are the takeaways from that? Let's see if I can get this through quickly. So the third part, statistically attuned algorithms. How do you have algorithms that tune the trading of reward and helping participants with statistical analysis? And this is a paper, also all these are working papers. So if you're working on related areas, please let me and my grad students know, just so they don't end up getting scooped or anything. And we're also happy to chat about this. The key idea here is that we want to combine a hybrid combination of assigning arms to participants, alternatively using uniform random, 50-50, or Thompson sampling. And I won't go into too many details, but you can imagine a fixed proportion of assignments. You have to set a parameter, 0.1, 0.2, always uniform random. But that will have the same probabilities before, right? Where you just always some participants end up in one arm, which may be worse. And probability clipping, as we mentioned. But the key idea is Thompson sampling posterior difference. How does it work? It's a data adapted proportion of assignments to the arms. And the key idea here is adapt phi of t, the probability of assigning them to uniform random, as the posterior probability, the arm difference is small, below a threshold parameter that a practitioner or scientist specifies where I can give up reward to get statistical inference.
Yeah. Can people consider versions of this model where the threshold changes over time?
Yeah, that's a good point. I'm pretty sure they have. Let me think I've seen. I think there's a paper on that I have to look into and see what the exact impact is. Yeah. So in terms of Thompson sampling posterior difference, I think the interesting question there would be, how does that compare to this kind of adaptation? What are the ways that you adapt it over time? And how do they depend on experimental design or other kinds of effects? Yeah. So again, Thompson sampling posterior difference, when there's zero small effects, great, do more uniform random, less Thompson sampling. Better false positive in power with minimal loss in reward. So trying to get a trade-off. When there are large effects, do less UR and more Thompson sampling. So again, the idea is with probability 5t, choose arms uniform random, 1 minus 5t, choose arms Thompson sampling. Where that's the posterior probability at observation time t, participant 50, 80, 100, the difference in expected mean outcomes is small, less than some threshold. So when probability of zero small effects is high, more uniform random, more Thompson sampling when probability of large effects is high. And that's the algorithm we can lay out there. So this is a plot that basically helps you understand the reward power trade-off, where we matched all the algorithms on false positive rate. So we chose parameters that match them on false positive rate, and you can see how they trade off power and reward. In general, Thompson sampling post-diff gives you better power. You can see it's these triangles up here. So in general, it's giving better power here at the expense of some reward sometimes. There are times when it does just dominate. For example, for particular effect sizes, 0.2, 0.3, 0.5, this is better in both power and reward. And you can understand the kind of key reason why. On average, we're seeing evidence it does better. But again, I think that's not the kind of right thing to look for. It's more understanding what context these make sense and what the pros and cons are of the algorithms. In general, I think both of these are doing better than either uniform random or Thompson sampling. But again, it's a subtle argument to make, but I think they're all doing better in the extreme of uniform random or Thompson sampling in terms of better balancing reward, false positive, and power. And the key kind of reason why is that it's adapting to the effect size in an appropriate way. So when there's a small effect size, there's a bigger one. This way, Thompson sampling posterior difference will better trade off and give you more reward when you care about reward more, and more power and more controlled false positive rate when you care about it more, because you're allowed to specify the kind of arm differences you care about. And so it's adapting in response to different scenarios. Does that make sense, everyone? Just having a fixed amount of uniform random. I have some considerations here for how you choose what a small difference is. And it's hard for practitioners to say that sometimes, but this is basically plotting if the true effect size, was 0 or 0.1 or point and so on, then how much does false positive rate change when you set your threshold near it? How much does power change and how much does reward? I think this is a nice set of plots because you almost have to give this to scientists to understand, well, I get a big bang for my buck in terms of reduction in false positive rates up to here, but then it starts to drop off. Power, again, big bang for buck as your small threshold pushes the true effect size. If you overestimate it, that's fine, but you just don't get as much benefit. With rewards a bit more constant. So these kind of analyses can help a practitioner understand, well, I don't know what the true arm difference or effect size is, but here's, for this particular algorithm, how my choice of the parameter is going to affect the behavior, whether it's my choice of small is above or below what the actual true effect is. And you can have insights like, well, you get a quick bang for your buck here, quick step up there, but then it starts to decline. So that can help inform them about what trade-offs they want to make. Because it's hard for them to always articulate how much you care about reward. Like, what's the multi-objective function for how much you care about reward for power? So what are your takeaways from this, about this algorithm? In terms of how it better trades off reward and power by having a step that does more uniform random when effects are small versus maximize reward when they're bigger, and in terms of the particular way we compare and contrast that to other methods. Okay. So just to summarize the review, we talk about empirically exploring. What are statistical issues in adaptive experiments? Increased false positive rate and reduced power for the beta Thompson sampling, and why that happens. Random lows cause biased estimates and reduced power, and the assignment of posterior property substantially favors one arm, even when there's no difference. We give examples of this broader framework of algorithm-attuned statistical tests. I've especially talked about algorithm-induced test statistics that allow you to control false positive rate by generating the, like, for example, an existing Walls test statistic where you simulate the distribution under the null where you use Thompson sampling. And that gives you good false positive rate, but it can have a big negative cost on power. And then we can look actually at allocation probability tests, which controls false positive rate, but by counting the number of times the probability of arm A being about 0.5, it's picking up on a piece of information that's being used by the algorithm in data collection. And that seems to give better discernment compared to something like the algorithm-induced test, because it's picking up on the key quantity that discriminates using null and the alternative. And that outperformed, or at least was comparable. I think arguably it outperformed some state-of-the-art approaches, especially because it didn't require probability clipping where you had to stop the probability at 0.9 or something, which can reduce the reward or benefit to participants. And now, statistically attuned algorithms. Give some examples of how you better trade off reward, statistical analysis, by adapting a multi-uniform random exploration, traditional experiments, be proportional, the probability arm difference is small. Parameters set by practitioners, and showed how that can give you a better reward power trade-off by being adapted to what the true arm difference is. In terms of ongoing in future, be happy to talk more, but I'm going to see above here is as people talked about, think about extensions to more than 3 arms. For the algorithms like Thompson sampling posterior difference, as well as particular tests, and especially thinking about something about factorial or multiple independent experiments, which are very important in the real world because most experiments just don't have effects. So we need to give people techniques where they can run many things at once, even if they don't look at interactions, to have a higher chance of detecting what's working or testing more hypotheses, accelerating the speed of science. I think that the real, ideal goal, holy grail is getting more accurate, however we characterize that, posteriors. Because if you know if you have a better sense of what the posterior is, 0.8 versus 0.2 and what the distribution might look like, then you can choose. I'm going to be conservative. It is a 0.8% chance that R may is better than B. I'm going to sign with 99% chance because I want to help people and I don't want to risk any chance. I could be wrong, but that's fine. Or someone else could say, well, it's 0.8 and 0.2, but I would assign 0.6 because I want to keep getting more data. So I think that would actually be that's what we're trying to focus on now in terms of getting more accurate sense of what the actual true probability of something being better is and how we even model and characterize that, because that allows people to then set how much they want to get more data versus try and optimize. And this is where I think, especially tying with literature on optimal experiment design, which doesn't normally think about this reward maximization, might be one framework we need to handle that. And there's some ideas about how to reduce bias, like burning periods uniform random instead of just running it. Applying inverse cultivating or other methods while it's running, so you can reduce bias in sample means. If we include uniform randomity, can we diagnose the degree of bias, whether you're in the world where there is a difference or there isn't? And some compensation for really stopping on multiple testing. And there are probably other things that are needed. I'm thinking about, as my optimal experiment design, when does this actually accelerate scientific discovery? For example, a 3-arm case or 4-arm case is one where, as you assign people, essentially better arms can actually increase power to detect which is the best arm because low performing arms fall out more early. So that could actually increase power. So you don't always have to pay a cost. And I think that's a really interesting question here is like, how do we actually get situations where we can show behavioral science, you can actually increase your discovery and help people. And when, of course, you have to trade these off. And how do we formulate these kind of multi-objective problems? It's not trivial at all to think of how to spell out how to weigh reward against power, especially when power depends on what the actual effect size is. So opportunities announcements. Anyone's welcome to come with Sign a Talk series. You can sign up or let me know if you want to present online. I applied for NIH, NSF, other grants using these methods. Most of my funding is actually in the US, even in Canada. So if you're interested, and we have a mailing list. You can join that, type that URL into your browser, tiny.cc join IR extended. I can pop by anytime or just offer to present. People want to come and visit or have us come here, it'd be fun. And there's a hybrid symposium on adaptive experimentation at GSM in Toronto. Okay, well, thanks everyone.
Thanks, Joseph, for this nice talk. So, are there any further questions?
I have a question about how the model works in the case, or how the algorithm works in the case of the beta intermediate model. So to start with, you model the probability of assigning arm 1 to a participant with a beta distribution, right?
Yes.
And then at the start of the experiment, let's say you just choose the parameters to be 1, 1, so it's uniform, and then draw a random sample from that. And if it's greater than 0.5, then that's fine.
Sorry, I'll clarify that. Actually, I have a question. I know it's weird, but so it took longer. Could everyone say all their questions? I can at least hear all the questions and answer them. Yeah, so that was a good question. So it's a question about how assignments working and how Thompson sampling works exactly. What are the questions people have? I just spew them all out and then we can at least hear them all. Yeah.
How do you get these past IRBs?
How do you get these past IRBs, right?
I understand from like production, because internal, certain things go by, if you're not going to publish with it, things like that, it's to improve your product. We've seen plenty of examples where companies are running experiments on people. It's been, Instagram is.
Okay, so how do we get these past IRBs, and also what are the ethical considerations here?
Yeah.
And what are the questions people have?
Okay, so maybe I have one question. So Here, it seems to me that the first part you talked about is the issue for best arm identification, if I understand correctly. It's not about regrets, as mentioned. Like I just want to understand, like, if it's about regrets, what is the result? And what is the motivation for best arm identification here in this setting? And why don't we consider some other sequential tests rather than characterize?
So I think the question there is, what's the relationship between what we're doing here with Thompson sampling, minimizing regrets or maximizing reward? How does that relate to the problem of best arm identification, which is assigning adaptively to figure out what the best arm is? And is what I'm doing something else or related?
Right. How
Yeah.
is it related to other ways to do best arm identification?
Yes.
Yeah.
Because I would say this isn't best arm identification. I think it's actually a slightly different problem we have to characterize. But I can answer more. What other questions people have?
How are you measuring the reward?
Yeah, how are you measuring reward?
I guess like if it's like obvious, like yes, no, it's helping or not.
Yes. Any other questions? Great, now I get to choose. Okay. So I can clarify quickly, but when you do Thompson sampling, you have a beta for one arm and a beta for the other. And then you actually are using those, you could do it analytically for the simple case. Given my beta distribution for one arm, beta for the other arm, what's the probability arm A is better than arm B? So just, you could calculate that analytically.
Okay.
But Thompson sampling, the nice idea is that if you just sample from each, you can then figure out which of those parameters maximize given your parameter sample, which arm would I choose to maximize the reward?
Okay.
And so that basically, if you sample that way many times, that basically gives you posterior probability of assignment.
Then do you update it in batches or after each individual?
That's up to you. Batch size can be 1 or can be 20. And that's a very interesting question that isn't often addressed as much in the machine learning literature, I think. Reward is something chosen by the experimenter. So what's the, is the explanation helpful or not? Did people learn from the setting? Did people walk more steps? So it's kind of something that comes in, and the adaptive experimentation is something to layer on top of that. But just, in a normal experiment, you can take your time choosing rewards. You can have 20 of them. In adaptive experiment, you make decisions. And so kind of adaptive experiments are interesting because it forces you to do your data analysis on the fly, which is a whole host of interesting issues. IRB, I think that's a whole good set of questions. What I would say is, I think we should argue that actually this adaptive experimentation could transform people to realize that like experiments aren't an unethical thing to do. And here's why. You might think the probability, I might think my probability of my talk being clear was, 99%, but I don't actually know that. If I think this Bayesian framework, what's the probability my explanation of a concept is really that good? And if we can assign proportionals explanations, maybe that's a way of helping people think about why we have to experiment to really understand if we know what's correct. And maybe it makes it very explicit to them that we can actually adapt over time in proportion. So I think it's actually arguably in some ways a more ethical way to do experiments. But I want to even step aside from that. It's unethical not to experiment. How am I so bold-faced to think that I know what the best explanation is with 99% chance? Because I'm experimenting right now. I give you 100% of one explanation, 0% of any other. When I explain a concept to you, 100% of mine, but 0% of his and 0% of hers. The point of best.
On the point, I mean, there's experiments that are different experiments with different goals. And Instagram's goal is to hook people. And well, to maximize profit, but the medium objective is to hook people. It's not necessarily, the optimal goal.
Yes.
We might be going for or whatever. I guess,
Understand. I'm still sort of re-skimming the transcript of what people said. Sorry, go ahead. Yeah.
Yeah, so I guess,
That's what I'm worried about. Usually people have to get consent to be experimented on. If we're doing this at schools,
Yes.
with minors in the US, things like that, that's.
Well, sorry, I should be clear. When we do randomized comparison, first of all, I think the word experiment, I should just ban use of that word for myself, but randomized A/B comparisons, adaptive comparisons. We do, of course, get ethics approval for that, and people consent, for example, as part of the course to receive different options. So that should be clear. Sorry, that should be clear. But I think you were asking a more general question, right? About how we think about the ethics of this and the fact that people will be resistant to it. And people are this psychological research is very resistant to the idea of like getting different options. Even if one option is worse, they almost prefer to get that option. I think I forget what the exact paper is, but I think in terms of objectives, it's a very good point. I think that gets to the point about outcomes and rewards, right? I think a question I would frame that as is, how do we do adaptive comparisons or experiments when we think there's only a correlation between our outcome now and the outcome we're going to care about later? If you think correlation is 0, don't adapt. If you think it's 1, you're good to go. What about it's 0.3 or 0.5 or 0.8? How do we have parameters of the algorithm that will modify it based on that? But back to your question, I think so best sum identification, this is also something reviewers raise often. Best sum identification, I think, is interesting and important, but I don't think it's actually the problem we're trying to formulate here. I think we're formulating a very different problem, and trying to characterize that mathematically is something that is challenging, but could be very powerful. When you're maximizing reward, you are just kind of saying, let me try to assign arms in a way that will give people the best outcome. And I think what we showed in the first line of work is that you could imagine that that could work for analysis data from experiments, or it could be okay. But it turns out that it does okay, but there are problems. That's where you get a higher false positive rate and a lower power. So if you try to maximize reward using an algorithm like posterior sampling, Thompson sampling, you actually get issues that mean that like it could potentially give you data that can be analyzed, but there's some issues. And that's where we come up with different statistical tests and modify the algorithm. So I think that's one line of work, right? The best identification problem, I think, is actually different. It's saying, how do I identify what the best arm is? But it doesn't actually think about the case when there's no difference in arms. When there's no difference in arms, that's actually really important knowledge, right? Like I want to know if your explanation and my explanation don't have a difference according to one outcome variable. So what I would say here is that I think a lot of this work is thinking about that question of, if you look at actual social behavioral scientists, they care about actually doing hypothesis tests or other analyses to understand, is there evidence for a difference between arms? And I think that's actually a distinct problem from the best arm identification problem, and one that we need to mathematically characterize better. And also, to be honest with you, to rethink. Like, I don't think I fully appreciated, till I started this work 6 years ago, that we actually really need a different framework for how to use data from experiments to make decisions. Because yeah, I mean, I know we had Bayesian stuff and people, of course, love it and talk about it, but I didn't fully appreciate that actually, when I run 800 people and do a hypothesis test and make that binary decision, there's value in that, but it's not quite the framework that's needed now, right? Because if I want to study with 100 people and you want to use my study results, you need something from me. You got data from me, right? But how to use your data, sorry, be concrete. I give expression A or B. I had some data. Maybe there's 6% chance, let's say, A looks better than B. And now you're going to run a study with similar explanations. How do you use my data to decide what you're going to do as a practitioner or scientist? So I think this adaptive experimentation framework, I don't see it as saying, here's the way to do things. I think it's more like, it's pointing to the fact that we need a different framework for how we think about making decisions from experiments. When we go into the real world and we collect across different settings, we will need different frameworks for thinking about how to do that. And we have to do those in a very user-centered design way. How will instructors interpret it? How will social behavioral scientists interpret it? What are their needs? Does that make sense? I'll quote something from like Michael Jordan's talk at like IMS, which was, maybe I shouldn't, okay. Which was, maybe one thing statistics to think about is a bit more of an engineering discipline, instead of supporting scientists. And that's super powerful because statistics has so much to offer. But yeah, if we think about ourselves as like engineering, what do we need to give as tools? Like human-computer interaction, user-centered design. What do we give as tools to like an instructor, to a doctor, to a social behavioral scientist? And again, like that software grant I mentioned, those tools may connect them. There may be a wizard that says, you can do this thing, that's okay, but click this button to talk to a machine learning person. But ask them about X and Y, but you have to click this button for a statistician. So how do we build communities to help people figure out how to use these techniques in the real world to make decisions? Thanks so much, everyone. I appreciate it. Any suggestion or feedback, send them along to me or email or anything.
Turn it back over.